Hey you all, I'm back. 2021 Chemistry 5070 paper 2. Chemistry 5070 paper 2. The cover is right here. Theory and total marks are 80. Okay, 80 right there. And you'll be given 2 hours. So let me get to question 5A5. I did the other 4 in the other video. So I'll do the last 4 here so that you can have shorter, easy to complete videos as you go through them. So question A5, sodium metal is kept under oil to avoid reaction of the metal with atmospheric oxygen to produce the ionic compound sodium oxide. Construct a balanced equation for the reaction of sodium metal and oxygen. Include state symbol. Sodium is a metal, oxygen is a gas. Write the gas as O2 because that's how it exists. This is molecular oxygen. Do not write O by itself. That would be elemental oxygen, which doesn't really exist. It's very highly unstable, so it always bonds to give you O2. Then the answer is simply, or maybe the product there is sodium oxide. So you have Na2, then O. So state symbol says it's an oxide solid, gas solid. This one dissolves in water to give you a basic solution. So now that's our balanced equation right there. Number B, explain why the reaction between sodium metal and oxygen is considered a redox one. Because sodium loses electrons and oxygen gains electrons. Remember, reduction and oxidation can be defined in a number of ways. Therefore, from the point of view of oxygen transfer, electron transfer, or hydrogen transfer, and even just by observing if there's any increase or decrease in the oxidation number or state of a given element or species. So sodium loses electrons to oxygen, meaning it gets oxidized, and then oxygen receives the electrons, meaning that it gets reduced. Okay, oxidation is the increase in the charge of a given species, which could be which is usually an atom or ion. Therefore, sodium, let me just get to the next question. State the balanced ionic equation representing the half reaction of oxidation process using the equation for the reaction in A. So look at this. The equation is this. So what really is happening here? Which one is being oxidized? That's what they're asking. So Na is one being oxidized. So with reference to this is our Na, and this is what is happening to the Na. It donates 2 electrons to oxygen. Okay, it donates 2 electrons from oxygen. And if anything, this is supposed to be 4. Okay, I messed up here. This is supposed to be 4. 2, that is 4. So if I was to do that, it means I have to change here. I make it a 4. Okay, I make it a 4 right there. Rubbing is not so good like this, but hey, I ain't no machine, and that's the fun of life. It's good to make mistakes and correct them. So 4, it means even here I have to do a 4-ish, man. Okay, as long as you're able to see where I'm passing and why I had to change. So you're having 4 atoms of sodium which become ions by giving up 4 electrons. Therefore, 1 electron for each atom. So there's an increase from being 0. This is neutral. It has no charge here, meaning it's neutral. Once its oxidation state or its charge climbs from 0 to 1, this is positive 1, then it has been oxidized. If it moves from positive, goes back to neutral by receiving electrons, then it has been reduced. That is why if copper 2, for example, copper 2 ions become copper 1, like in the test for reducing sugars. They're called reducing sugars because they change copper 2 to copper 1. So hopefully I've gotten the picture. This is the oxidation reaction. 4 atoms of sodium donate 4 electrons, 1 from each to oxygen, and what really happens is this: they develop charges, and these charges attract them to the negatively charged oxygens who receive the electrons. Okay, let me move. 6. Use the periodic table to answer the following questions. I used my periodic table. So state 2 nuclides in period 3 that have the same number of neutrons. So sodium and magnesium, they're actually next to each other. 23, this is the number of protons or atomic number, mass number. How do you find the number of neutrons? You simply subtract. So 23 minus 11 gives you 12. That will be the number of neutrons. Then 24 minus 12 gives you 12. So both of these nuclides have the same number of neutrons. Okay. Then number B, give the name of the element in group 5 and period 3. The name is phosphorus. Allow me to just flip this paper. I flip the paper. So when you look at this periodic table, I'm running out of light. Hopefully you're able to see. So when I flip this paper right here, this is our first period here on top. Okay, first period, second period, third period. Okay, this period continues even on this other end here. And then groups, that is group 1, 2, which is this one, then 3, 4, 5. So group 5, then third period. So 1, 2, 3, group 5, third period. 1, 2, 3, that is period 3. Then group 5, 1, 2, 3, 4, 5. That's phosphorus. That is phosphorus. My answer is phosphorus. Question C, give the name of the most electronegative element in group 7. Give the name of the most electronegative element in group 7. Sorry, I'm moving the paper right there. The name is fluorine. Most electronegative, meaning that an element that is more likely to form an anion or a negatively charged ion. An element that has got high electron affinity, that's fluorine, because as you move up, let me just flip the paper. Okay. So as you move up, this is our group 7. The higher you move among nonmetals in a given group, the more reactive the elements are. And nonmetals usually gain electrons. They share and they gain, they don't give out. So the topmost here is fluorine, the most reactive nonmetal. These guys are noble gases, they are stable, and they have a lot of self-respect. So our answer there is fluorine. Then the next one is D. State the chemical formula for calcium selenide. Calcium selenide. Selenium is in group 6, its valence is 2. Calcium is in group 2, its valence is 2. So the atomic ratios of the two would be 1 to 1. So this is calcium selenide. State the number of metals, if any, in group 6. In group 6, allow me to flip the paper. Before I go there, allow me to check on calcium. This is calcium, group 2, valence is 2. Then selenium is somewhere here, okay, group 6, meaning it has a valence of 2, just like sulfur, just like oxygen. So the ratios would be 1 to 1. Then they're looking for the number of metallic elements in group 6, if any. You have to know that there is what you call the stairway or the zigzag. This zigzag starts from here. It demarcates it's a boundary between metals and non-metals. So you have it begins from below boron or between boron and aluminium. It goes like this, the staircase. On this side going up, let me just draw it up. You have the metals on top, the non-metals on top. Then this side you've got the non-metals, then down here you've got the metals. And then some elements that are found along these are called metalloids because they've got both dual properties of somehow being metallic and again being non-metallic. But on this side, these are metals. So in this group here, polonium. Polonium is the metal and it's the only one in that period. Above polonium, we're going to this element here, which is tellurium, which is a non-metal. So my answer here is 1. State the number of metals, if any, in group 6. That is 1. Okay, 1 metal. I move. Sodium chloride solution was electrolyzed using the experiment arranged as shown. This is the negative, that's the positive. This is your, that is your positive is the anode, that's your cathode, the negative side. Write down the formula of the ions present in the sodium chloride solution. This is a dilute solution, so you're having sodium, chlorine, hydrogen, and hydroxide ions. There are 4 of them. These 2 are the ones making up water, but because of it being in aqueous, the water is regarded to be in form of these ions. Number B, what observations would be made at electrode Y, which is our cathode? Bubbles of gas will be emerging. That would be the only observation. You don't say oxygen is produced. What? No, you just look at what would you see? What would the monkey see? What would the chicken see if you showed it? It would see the bubbles. It won't know whether it's so. You talk about or you write about what you'd be able to observe, because you can't easily tell what type of gas it is. Number C, write an equation for the reaction that takes place at electrode X, which is our anode. Okay, our anode. At the anode, out of said, hydroxide ions are attracted, but I just took it as water is broken down to form oxygen, and protons are given out, and so are electrons. Okay, and so are electrons. Electrons are negatively charged, so they travel upwards, going to the battery. Then from the battery, they flow into the solution. As they come into solution, what moves out of the solution? The electrons that flow out of the solutions are what? The number of electrons that flow to the battery is the number of electrons that leave the battery into the solution. Okay, into the solution. So when you look at the electrolysis of dilute brine or dilute salt solution, sodium chloride solution, this is also an option. There is very high likelihood that chlorine would also be discharged. That's why I was almost rushing for this. But I realized that this is more likely to take place, even if there are chances of this taking place, but this is also very likely to take place. But if the solution is concentrated, then this would have been our equation where chlorine gets to be discharged. In a concentrated salt solution or concentrated sodium chloride solution, water will not be discharged, oxygen will not be discharged, but chlorine would be discharged. So I spared this. So I had to plug in this one because it's the one that is very likely to take place when the sodium chloride solution is dilute, like here, dilute sodium chloride solution. So what difference would be in the experiment if concentrated sodium chloride was electrolyzed? Then the main difference that would be there would be chlorine gas would be generated at X. Okay, chlorine gas would be generated at X, while at Y it's just hydrogen throughout, hydrogen gas throughout. Whether it's in dilute or concentrated, hydrogen gas would be given out. So my last question there is, explain why solid sodium chloride cannot be electrolyzed. It is solid. It does not, or it cannot conduct electricity. It cannot conduct electricity. My last question in this video, which is question 8, is about the Haber process. Ammonia production. Ammonia is manufactured by the Haber process according to the following equation. This is the reversible equation, or an equation representing a reversible reaction. And this equation this reaction is exothermic. How do you know? There's a minus here. The minus represents that, or signifies that energy is given out in form of heat. And each time 2 moles of ammonia is formed, 92 kilojoules of heat energy is given out. So the minus represents direction of heat, meaning out, it's given out. If it's positive, it means, or there's no minus, it means the heat is taken in, meaning endothermic. A, the reaction reaches a state of dynamic equilibrium. What is meant by dynamic equilibrium? My answer there, my explanation is the rate at which the forward reaction becomes equal to the rate of the reverse reaction. Or maybe let me say the point at which the rate, okay, of the forward reaction becomes equal. Dynamic equilibrium is the point at which the rate of the forward reaction becomes equal to the rate of the reverse reaction. Can I write that one down? Dynamic equilibrium is the point at which, let's just say the point at which the point at which the rate of the forward reaction becomes equal to the rate of the back reaction. And this is observed in the arrows. These arrows are of same length. If one is short, it means the rate is lower. Now they are of the same length, meaning that it's at equilibrium. So length signifies rate. Then the half heads, or these heads signifies direction of the reaction, whether forward or backward. B, at equilibrium only 10% of ammonia is produced. B1, describe how ammonia is separated from the 90% of unreacted nitrogen and hydrogen. It is condensed. Ammonia easily condenses, but again it easily evaporates. So it is condensed into liquid and tapped out, or removed, therefore tapped out or drained. B2, state what happens to the 90% of the unreacted nitrogen and hydrogen. The gases are recycled by channeling them back to the reactor. Where they get to pass over the catalyst at appropriate pressure and temperature. Then they tend to be, they're made to go back and form more ammonia. So they are recycled by channeling them back to the reactor. The last question, or the second last question there, is C. Complete the energy level profile diagram for the formation of ammonia from nitrogen and hydrogen, indicating the activation energy EA and enthalpy change delta H. This is delta H. So we're given this, and then I had to put this. I haven't really written them according to the ratios like a balanced equation. I've just put the reactants, then products. I could have written reactant here, then product there, but I've chosen to put the actual species. So the reactants are here, and then I have to show that there's some activation energy that needs to be overcome. There's an energy barrier that needs to be overcome for ammonia to be formed. Ammonia, since the reaction is exothermic, the level of the products has to be lower because energy is lost. So initially the products have got energy at this. Remember, this is the enthalpy, this is the amount of energy in the substances or the reactants and the products, but here the energy is higher, but here the energy is lower, meaning energy is given out or lost. So I write it like this. This is the energy barrier, and this is our activation energy. Okay, our activation energy, which goes up to the level or the limit where the energy barrier is. Then the difference in the energy between the products and the reactants, or reactants and products, is my enthalpy, the amount of energy lost. So that's our energy level profile diagram. I could have also labeled this on this other side. I could have put this on the inside here. It's still the same thing. My last question is, explain why manufacturers avoid high temperatures like 1000 degrees Celsius to increase the yield of ammonia. The forward reaction in the Haber process is exothermic. So if you increase temperature too much, you are going to suppress the forward reaction, the top arrow here that produces this. So you actually reduce the yield of ammonia significantly. I end here with this section. I'll do the other questions in section Section B, one by one, but for now, I say to you, peace. Okay, peace.